13 of CF302 data structures. In this lecture, we are going to see another application of STAP, which is recursion. And we are going to see what is a recursion and what are the types of recursion available in literature. So let us start with it. So what is a recursion? Recursion is when a function calls itself. So I have written a small program here, the classical program of factorial of a number. So if we want to write the usual way of writing the program, then here this is a function fact which returns an integer value, and I pass the value in for which I want to find the factorial. So if I want to find the factorial for 5, that is 5 factorial, then I will be passing here 5, that is n is equals to 5. And then I is the counter, initialization of the fact which is going to store the ultimate factorial result. Now this program can be written, the loop can be run from I equals to 1 to n, or it can, that is I equals to 2 to n, or it can be from n to 2. I have written n to 2 because usually our factorial concept is like this. So it is equals to 5 into 4 into 3 into 2 into 1, but since 1 is already, we know something multiplied by 1 is 1, so I am omitting that. And it is fact into I, and because my function is returning an integer text, I am returning fact. So here if we look at this function, what happens is that here fact is the function which is to be called by the calling function, and then when we enter the fact, it is a usual line of statements, and ultimately the fact result is returned. But what happens if we want to write a recursive program? So what is a recursive program? Where a function repeatedly calls itself. Now let us see how this actually works. So if we want to find out what is the logic of recursion, if we want to find out 5 factorial, this can be written like this. So 5 into 4 factorial, because this is 4 factorial. Again, if we have to find out 4 factorial, we can write it like this: 4 into 3 factorial. Because this 3 into 2 into 1 is a 3 factorial. Again, if we want to find out 3 factorial, we can write it like this: 3 so we can write it like this: 3 into 2 factorial. And if we want to find out 2 factorial, then it is basically 2 into 1 factorial. So now 1 factorial, because if n is equals to 1, then the factorial value is 1. So this is the logic which we are going to use if we want to write a recursive function for fact. So what happens if I can write it like this? So if this line, I can write it like this: 5 into fact of 4, because fact is the function which is going to give me the factorial value of n. So if I can write it like this: 5 into fact 4, and then when I come to this, that is fact 4, I can write it like this: 4 into fact of 3, because fact is the function which is going to give me the factorial of our number. So I can write it like this. Again, this can be written like this. So this part we can write it like this: 3 into fact of 2 and this we can write it like this: 2 into fact of 1. we stop right here. So if we look at this, what we are seeing, so what do we see? We see that if we want to find out the factorial of a number n, then that can be transformed into a form where we can represent it in the form of the lower order factorial. So if we want to find out the factorial of 5, we can transform it into fact 4, where 4 is one order lower than 5. Similarly, fact 4 can be represented like this and so on. So in general, we can have something like this. So we can write, in general, we can write like this, that so in general, we can have something like, to find out the factorial of a number, it can be represented like n into fact is the name of my function, n minus 1. So we can represent it like this, n into fact n minus 1. Because at this stage also my n value is 5 and fact 4. So we can, fact 4 means it is 5 minus 1, so n minus 1. Again, if we want to find out the factorial of 4, we can write 4 into fact n minus 1, that is 3 and so on. So this is going to what? This is going to be what? We can represent the factorial in terms of n minus 1. Now, a factorial, so all recursive functions have two things. One is known as the base case and the other is known as the recursive case. So in case of the factorial program, our recursive case is this one. So what we have to do, we have to keep on repeating n into fact n minus 1. Now what is the base case? Base case means when this recursive case will end. Because if we see that without a base case, if this program, if we write the factorial program using this, then it will keep on repeating. It will go till n minus 1. N minus 1 means it will be going to the minus and then come back to the highest integer value range, and it will keep on repeating like this. So what is a base condition? So base condition is basically used for termination of the recursion, that is where it will be ending. So if we think, like in case of my factorial program, what will be the base case or the terminating condition, we can tell that for factorial program, it will be what? We can write it as if n is equals to 1. That means if my n value becomes 1, then what will be the terminating condition? My program will end, because we know that any factorial is n into n minus 1 into, so it's basically like this, n into n minus 1 into dot, how far it will be going? Till 1. So if we reach, so when n becomes 1, by doing n minus 1, we know that we have reached the end and we can stop. So keeping these two things in mind, let us write the factorial program now. So the same thing, there will be no change in the prototype of the function. So it will be same. Now what is happening? If, so first the base condition. So if my n value is 1, then what do? We return. We return 1, because we know factorial of 1 is 1. Else what we do? So if my value is not 1, then what we have to do? We have to keep repeating the recursive case, that is return. So we write a return here itself, n into fact of n minus. So this is the end of our program. So no change in the prototype of the function, but internally we put a base condition. So this is my BC, that is base case, and this is my terminating case. That this is my recursive case. That means if my value is not n, what I need to do? I need to keep on doing this. Why return? Because if we return this, so what happens? Let us see now where stack is used. Why recursion? We already know that in function call stack is used. Now what is the picture of a stack if we are using recursion? So suppose my n value is 5. So I am trying to find out the factorial of 5. So at first stage, this function will be called with the value 5. So at the very first stage, so it will come inside, it will check whether n is equals to 1, no. So it will come to this part. What happens here? It is n into fact n minus 1. Now we don't know, so basically it is 5 into fact of 4, but we don't know what is the value of 4, fact 4. So what happens? This gets pushed into the stack. So it becomes like this. 5 into fact 4. It gets pushed into my stack. After that, so now what will be done? Again, fact will be called, but not with the value 5, but it will be called with the value 4 now. So again, the checking whether n is equals to 1, no. So it will come here, and now what we have to do? What is the value of n? Now the value of n is 4 and the value of n minus 1 is 3. So what happens? Again, this is unknown. Fact 3 is unknown. So again, it will be pushed into the stack like this. So 4 into fact 3. Because we know that in case of function call, if a value execution is halted when a function gets called. But what happens in this case? Here what is happening is that for this particular function, because this fact 4, fact 3, they are unknown, so we have to push it into the stack because we have to find out first that values and then only they can be called. So next time when it will be called, then this is no more 4. So this is 3. So n is 3 and n minus 1 is 2. So in the stack it is 3 into fact 2. Again fact 2 is unknown, so it will be again the function will be called. So at this moment it will be called on the value 3. At this moment it will be called on the value 2 because n is 2 now, and it will be 2 into 1. So again, so we need to find out the value of fact 1. So it will be fact 1. So still this stage, it will be in the stack. Now what is the value of n? The value of n is 1. Now when we come to this part now, it will go inside. Now it is matching with my base case. So what it will be returning me? It will be returning me 1. So once it returns a 1, where it will be returned? It will be returned back to the stack. So this is my stack where this value is going to be returned. So it is going to be returned here. So it becomes 1. So what happens basically? 2 into 1 is 2. This value gets calculated and it pops out. And then we know what is the result of fact 2 is 2. So here it becomes 3 into 2, 6, and this 6 gets popped out. At this stage it is 4 into 6 and the value is 24, so it gets popped out. And then it is 5 into 24, which is equals to 120. and it gets popped out. And when it gets popped out, this value is returned to the calling function. So 120 is returned to the calling function. So this is how stack is made use of when we are using recursion. But you should remember that whenever a function gets called, stack gets used. So suppose I am writing this program within main. So I'm writing a main and I'm writing int 10. And then I'm calling my recursive. Okay, let me write it at the top because otherwise you have to define the prototype. So int 10, this is my recursive function. Okay. And then my main function, what I do, I simply write a printf. So I can write it like this, %3. And I can simply call fact in because that is returning me the value. It is returning me an integer value, so I can safely write it like this and I can exit. So this is my factorial program in total. Now what happens when the execution starts from main? So I told you whenever we reach this line, so from printf the execution starts from right to left. So whenever it comes to fact 10, the operation of main is halted and it is pushed into the stack. So main is pushed into the stack and the control comes to fact. So fact main execution is halted, it is pushed into the stack and the execution comes here. And then that stages are taking place. So it is first 5 into fact 4, 4 into fact 3 and dot what we have seen. Now whenever from here that 120 value will be returned, it will be returned back to the main. Main will be popped out, the execution, it will show you the value and it will execute. So this is the whole recursion. This is meant by a recursion programs. I'm not going into the details of some other programs. You can try it down on your own. Now recursion makes a program little bit, it makes a program short, but it takes little bit longer time because of this the length of the stack. The length of the stack increases in case of the recursive program. So when the stack size increases, that means it consumes more memory space because each of this represents a memory space. Either you implement with the help of array or linked list, still each of this represents a memory space. So it do consume more memory space if you are writing a recursive program. Now let us say why the base case is required with the help of this example. See, when we call this, when we write this kind of recursive function, suppose we have not written this line. That is, we have omitted this base case. So the only statement which is there will be this statement. So if we represent that, if we show what happens in case of a stack, so first main is called, and then fact10 is called. So main execution is temporarily suspended and put into the stack, and then this change happens. So it's basically fact10. So fact n is called. So when fact10 is called, then this is pushed into the stack, that is n into fact10 minus 1. Then we have to find out fact n minus 1. So the next state is n minus 1 into fact of n minus 2, and this process keeps on repeating. So when this process, like this, these elements are pushed into the stack. Now, if we don't put a base case, then this will keep on repeating, like n minus 2 into fact n minus 3, n minus 3 into fact n minus 4, and this will keep on getting pushed into the stack at the top. If we don't put a base case, then what will happen is that eventually this stack, whatever is the size of the stack, this will get overflow. So basically the error, you can try it out in your home by running the program. So if you don't put the base case, what the error you get is known as a stack overflow. And this error you will get during a runtime. So this is basically a runtime error. Why this is a runtime error? Because when you are writing this code, the compiler has no issue with whether you are giving the base case or not giving. So it will completely run fine, but when the program will start executing, the stack will get, the elements will get pushed into the stack like this. And when you are not putting a base case, so this is going to go on an infinite number of times because the program doesn't know where to stop. And then it will lead to a case which is known as a stack overflow. And stack overflow is basically a runtime error. So this is a runtime error. So because of this, for any recursive programs, what is absolutely necessary is to write the base case. So this is absolutely necessary, that your recursive, any recursive program should have a base case. Now let us go and check what are the types of recursion available. So recursion can be, the types of recursion can be defined on three things. One is on the function call. So how the function call is happening, based on that we can have a direct recursion or we can have an indirect recursion. I will come to it. I will come to each one of them with example. The second is on operation. That is, the operations are like multiplication. In case of the factorial program, we can talk about the operation to be multiplication. So whether the operation is pending or it is not pending, based on that we can define non-tail and tail recursion. And based on the structure of the calling pattern, that is how the function is being called. So this is on the function call, and this is on the structure of the calling pattern, how the calling is happening. Based on that, we can have a linear recursion or we can have a tree recursion. So these are the types of recursion. Now let us come to each one of them, that what I mean by direct or indirect recursion, non-tail and tail recursion, and linear and tree recursion. So let us see how the recursion is typecasted into on function call. Now let us see the first example, which is this one. So in this case, what is happening, we are seeing, so it is int10, and it is a normal type of recursion what we have seen in case of a factorial. So here there is a function, that function is calling, so this is a fun and it is calling itself. So within this function fun, it is calling itself directly. That's why this kind of recursion is known as a direct recursion. So this is made by a function call. So this is the way the function fun is calling directly itself. Now if we go to this example, see there is a function fun1. What fun1 is doing is calling fun2. So this function is calling this function. And then when we are going to this function, then fun2 is calling fun1 back. So fun1 is calling fun2 with the parameter n, and when we go to fun2, it is calling fun1 with x minus 1, that is with the value n. So if n is sent here, this will be n minus 1. So this is also a recursion, but this is an indirect recursion, because where the recursion is happening at this place. Why? Because fun1 is calling fun2 with the value n, fun2 in return is calling fun1 with the value n minus 1. So ultimately when it comes, so let us check a value, let us check an example and see what is happening. So let my n value be equals to 3, the smallest example. So when fun1 will be called, so 3 is sent here, is it equals to 0? No. So what will be called? Within fun1, fun2 will be called. So let us at the same time, let us have the stack. So my fun1 is calling fun2. So fun1 execution will be suspended with the value 3 and fun2 will be called. So when fun2 is called, what it is calling back? Fun1. So fun1 x minus 1, that is fun1 2. So here the value becomes 2. Now when it is called back, then again this execution will be suspended because it is dependent on a value. So fun2, now what is calling fun1 2. So when fun1 2 is happening, then it is again coming, because it is not equals to 0, to again fun2 2 will be called. So what is happening here? So fun1 2 will be here. Again when it comes here, it will be called with fun2 2, and what it is going to have now, the value 1. So it is calling back fun1 with the value 1. So again this will be pushed. Fun2 2 will be pushed into the stack. So this is repeating. Again it goes here, so it is not equals to 0, to again fun1 will be pushed into the stack. It will come here, and again fun2 will be pushed. So here fun2 will be pushed, and this process keeps on repeating. Now its value becomes what? It is no longer this value, so it becomes now what? 0. Now when it comes here, it returns n. So here it will be returning me 3, but when it returns me 3, what happens? All will be popped out of the stack. It is returning me 3, so it will be returning me 3 to where? To the first, fun0. Then fun0, then fun1, then fun2. In this way, this will keep on repeating. So we see here, it is also creating a kind of recursion, because the value is decreasing and we are reaching a base case, but the function is not called directly, rather it is called via another function. That's why this is known as the indirect recursion. So that is why it is known as on function call. So the recursion is happening, the differentiation is happening on the way a function is calling itself. Either it is calling itself within the function itself, or it is calling with the help of another function, and that distinguishes between the direct and the indirect recursion. Now let us go to the next one, how the recursion is distinguished between the based on the operation. Now let us see how on the operation the type of recursions are defined. So this is our usual, on the left hand side is our usual factorial program which we write. And here at the last step, there is a thing which needs to be noted. And what is that? That is this line, n into fact n minus 1. So multiplication is the operation which is to be performed. Now this is a pending operation. This operation is known as a pending operation. Why? Because if we look at the stack, we cannot find out 3 into fact 2 until we find out what is fact 2. So this result, so what is equal to this result is unknown until we find out fact 2. Similarly, 2 into fact 1, we cannot find out until we find out fact 1. So this is known as a pending operation. Whenever a recursive function has a pending operation, which depends on the next function call, because 3 into fact 2 can be find out only when we find out fact 2. So this is another recursive call to fact. So again, 2 into fact 1 can be found only when we can find out fact 1, which is a recursive call to fact. So whenever there is a pending operation during recursive call, that type of recursion is known as a non-tail recursion. The non-tail recursion can be defined as, so non-tail recursions have pending operations during function. So this is the non-tail recursion. We can convert a non-tail recursive function to a recursive function as I have shown you on the right hand side. So how we can do that? So let us see. So here is my factorial program with the value n, and here instead of calling factorial within itself, I am calling another function which is known as fact1 n minus n comma 1. So here for my given this particular value n3 comma 1 will be passed. Now when I come here, it is 3 comma 1. So if n is 1 means it will be returning the fact. That means if n is 1 means my factorial result will be equals to 1, so it is going to return me this. But if this is not the case, what it is going to do, it is going to have a call, recursive call to fact with the value n minus 1 and I'm not telling along with the operation, but it is the n minus 1 and the result n into fact. So at first time, so it is 3 comma 1. So now what it is, there are 2, and what is this result? 3 into 1, which is equals to 3. So next time when fact 1 is called, then there is no dependency on this value. So there is no dependency on the another recursive call. What will be stored in the stack? Yes, in the stack, what will be stored is that 2 and 3. Because fact 1 is getting called again, so these two values, 2 and 3, will be stored. Now this value is a standalone value. So there is now, let us see why it is as, so this is known as a tail recursion. In tail recursion, there is no pending operations. Why there is no pending operations? Because we see that we will distinctly see between these two. In this case, there is a dependency on the recursive call for finding out the result of each step. Well, in case of a tail recursion, we see that the recursive call to this function has no dependency. We are simply sending two values. So once we have done this, so what happens? So this value will be 2 and 1. And when we come down here, this value will become 1 because n minus 1 is 1. And what is the value of n2? And what is the value of fact? So fact, what I have sent is 3. So this was what I have sent, 3. So it is going to give me 6. So next, what value gets stored? So the system stack do gets occupied with values, but that values are values for the n and the fact, that is the result. Now next time when it is happening, so this value will be what? This value will be 1 and this value will be 6. Now because n is equals to 1, so it will be returning me as 6. And where it will be returning me? It will be returning me to this function fact, and it will be giving me the result. But now the question is, when we are calling from main, which function? Now the recursion is happening here. So this is the recursive function. This is no more the recursive function. Recursive function is this. But when we are calling from the main, which function should we call? Should we call fact1 or should we call factorial? The answer is, we will be calling factorial. Now, if we look at this example, again, this is a kind of, now this is not, we cannot classify this into direct or indirect, because in indirect function call, fact1 should have called factorial. But this is an example of tail recursion, where by adding an auxiliary parameter, so fact here is the auxiliary parameter, to a function, we can convert the operations pending for the recursive call to a non-pending operation. So when we have to call within main, what we are going to call is basically the factorial function. So we will be calling the factorial function with the given value of n whatever, and this is going to happen. So this is the difference between a non-tail recursion and a tail recursion. Definitely, the non-tail recursion makes the program lengthier in size, and in most of the places what we used is the non-tail recursion only. And this fact is known as the auxiliary parameter, and this function is known as the auxiliary function. Now let us see how, based on the structure of the calling pattern, we can differentiate the recursion type. Now let us see these two examples. So this is my factorial same function, recursive function. Now here, if we suppose n is equals to, let us suppose n is equals to 4. What happens? So the first call is n into fact 3, 4 into fact 3, 3 into fact 2, 2 into fact 1. Now this is known as a linear recursive function. Why linear? Because here we see that the multiplication operation is dependent on only one call to the recursive function. So only one side of the operation is dependent on the recursive call to the function. The other part is a constant. So this is known as a linear. So this is known as a linear recursive function. If I compare it with the Fibonacci, so this is my Fibonacci. So for n equals to 4, what we can write? Fibo 4 is dependent on Fibo 3 plus Fibo 2. fever 3 in return is dependent on fever 2 plus fever 1. Fever 2 is dependent on fever 1 and fever. So in case of the Fibonacci series, we see the operation is plus, and both sides of my operation have a recursive call to the function figure. So this is the example of a free recursion where, or we can also call it a nonlinear recursion, because the pending operation, so this is my pending operation, and the pending operation is dependent on pending operation is dependent on two recursive calls. Because if we, in this case, if we have to do the multiplication operation, we can find out the result with the help of only one call. Well, in this case, if we have to find out the result of fever 4, we have to do two recursive calls to my function. So naturally, the system stack occupies more space in case of a tree recursion than a linear recursion. So we can have it in form of a tree. So I'm simply writing 4. So 4 is having a call to 2 and 3. So this is my F. Let me write it down in short. F4, function call to 4. So this is dependent on this 2. This is further dependent on fever 1 and fever 0. Now fever 1 and 0 is not broken down because they are part of my base condition. Now fever 3 is dependent on two calls. One is fever 2 and another is fever 1. Fever 2 is again dependent on 2, fever 1 and fever 2. So we can draw this in form of a tree. So this is known as a tree recursion. So this is known as a tree recursion or nonlinear recursion. Well, if we see this example of linear recursion, so it is basically there is a, we can draw it like this. So fact, I'm writing it as FF, fact 3 has two parts. One is the constant 3 and the other is the fact 2. And then this is a call to 2 because 3 is a constant. So 2 into fact 1. So basically it is dependent on fact 1. So if I redraw this, it will be looking something like this. If I draw the dependency diagram, this is the dependency diagram which I have shown you. So the dependency diagrams looks like this. So f of 4, that is this function f, is dependent on f of 3, is dependent on f of 2, and is dependent on f of 1. So linearly it is dependent, where in this case there is a relationship, and that's why this is true. So this ends the lecture on recursion. Now we will be seeing some examples of recursion in real life.